action. Okay, guys, we're building batteries well, it's not for real. We are building batteries today on paper, and then we will be building batteries for real in lab. So guys, let me orient you to the pages that I gave you. First of all, this is going to be our schematic of a battery. This is going to make some of you wildly uncomfortable. Well, most of you won't know the difference. But guys, what we're going to do is this is basically going to be all your notes today. But what you're going to see, if you either did or will print the notes, is we are going to skip pages of information that are in the slides. It's not that we're not going to cover the material. What we're going to do is we're going to condense all the material and the math on here. So if you're going back and if you're looking at the slides later going, wait, we never looked at these slides, what I would encourage you to do is look at this and then ask yourself, is there anything in those slides that we didn't cover here? And you're going to find that the answer is no. So the reason that I leave that material in the slides is because it's simply like a more detailed covering, if you will, explanation of what's going to go on here. Does that make sense? Okay, so now guys, we've got to talk about this. Grab this thing. So guys, this is no longer on the AP test. This used to be the right in the middle of the AP exam, and I don't mean that it was like question 26. It was right in the middle in that it was central to so much of what happened on the AP exam. In 2014, they got rid of this. And guys, when they made us aware of that in the 2013 summer meeting, I mean, it sounds weird, but I mean, they said, and no longer will we give your students reduction potential tables. And everybody's jaws dropped. And we were like, wait a second, are we not teaching electrochem anymore? No, you are teaching electrochem. Wait a minute, do they not have to be able to calculate cell voltages? No, they've got to be able to calculate cell voltages. Wait a minute, do they not need to know if things are weak or strong oxidation or reducing or oxidizing agents? No, they still need to know that too. And frankly, our response was that, why take this away? Because guys, all the answers are on here. So frankly, all that they've done is they just recondense things, and instead of giving this to you in table form, they will implant the few of these that you need to know into the questions. I don't know why they think that's better. To me, it's just stupid. But guys, this information will be on the AP test, but it will not be the whole table. It will just be the select few of these that you need to answer any particular question. Does that make sense? Okay, so guys, with that said, let's spend a little bit of time here and let's talk about what this table is. So guys, mentally cover over the title of the table and then allow your eye to scan down the table and talk to me about what you see given what you learned on Monday. What do you see, Matt? Good. So these are half reactions, and guys, forgive me, it's obvious, but it's important. So guys, what are half reactions? What do you remember about them? Go ahead. So what do half reactions represent? Half of a redox reaction. One is oxidation, the other is reduction. Good, but they're not. These are all not oxidations. What are all of these? Reductions. So guys, with that said, now mentally uncover the title and read it. Guys, this is a standard reduction potential chart. So now link the title with all of these half reactions, and what do you now notice? They're all reductions. How do you know that they are all reductions? Where the electrons are. What does reduction mean? Gaining electrons. And where are the electrons in every single one of these half reactions? on the left, on the reactant side. Are you guys tying all this together? So guys, what you have in front of you is a table of reduction reactions. They're all half reactions, and we know that they're reductions because the electrons are on the reactant side of these half reactions. So now allow your eye to go all the way to the right, and let's talk about that far right-hand column. Guys, what does that say? What are we given over here on the right? So we're giving an E in energy. You're going to find out later that it's actually an electrical potential. That's what that E stands for. What are the units? Volts. So guys, we are going to talk really quickly right now about voltage. So guys, this is your 90-second voltage introduction. You ready? So when you think about voltage, you may understand a couple things about voltage. So first of all, oh man, I'm out. So you guys know about 9-volt batteries, right? So 9-volt batteries are the guys that look like this. They're cubes. One side looks like that. You know what I'm talking about? So guys, you understand things about voltage because you've probably heard of 9-volt batteries. Now guys, what about the voltage that comes out of our wall plates? That's 110 to 120. So guys, it's actually 110. So this is 110 volt current. Batteries, the square batteries are 9 volt current. What about AAAs, AA's, C's, and D's? Do you know? 1.5 volts. Did you know they're all the same? Guys, AAAs, AA's, C's, and D's are all 1.5 volt batteries. So you've at least heard of voltage. The question is, what is voltage? Guys, let me define it for you really quickly. I don't think you need to write it down, but this is the idea. Voltage is pressure. Okay? Keep that in mind. Voltage is pressure. So let me put that in context for you. Guys, if you want to understand electrical currents, think about the flow of water. You ready? So guys, the idea is this. Why does our water, when we turn on this faucet, why does that water have pressure? There's more behind it. But guys, if the more behind it is not in a very specific location, it will not have pressure. Where is that water? Where's the water that comes out of our taps? You guys not know this stuff? Good heavens, how do you survive? Go ahead. Yeah, guys, okay. Yes, guys, our water comes from the mountains, and that's important. So let's pretend that all of our drinking water comes out of Deer Creek Reservoir. That's not completely true, but a lot of it does. So guys, the water comes down the Provo River, and where does it end up? It ends up in that water treatment plant that's up above the cemetery on 1600 North. You know what I'm talking about? There's a water treatment plant up there, and they take all the critters out of the water, and then they store that water in tanks. The idea then, guys, is that when you open the faucet in your house or in my lab, when you open that faucet, you are literally draining that tank that sits up on the hill. Hey, Matt. No. Oh, it may be. Well, I don't know. Brittany might be over there, but if not, there's the key. So guys, really that's the case. So the only reason water flows out of our pipes is because that water is sitting up on a hill. What if that tank was sitting out in the parking lot of Orem High School? The water would flow in the other direction from here. Guys, water always flows downhill. Sounds a lot like Gibbs free energy, right? Things always flow downhill. So guys, the only reason that water flows out of our tap is because we store it up in a hill. Now guys, here's the thing. What do they do in Nebraska where there are no hills? They have water towers. Have you ever seen this? If you've ever been in the Midwest, the first thing you see when you come into town is the water tower. How do they get the water up into the tower? They pump it. Guys, understand, we do not have to pump our tap water. It saves us thousands of dollars. Our water here is so cheap because, first of all, it's relatively clean because it's melted snow, unlike Nebraska where it's the stuff that's flowed down from anyway. But then, guys, they have to use an electric pump, literally, to pump the water up into the tower. Here in Utah, we don't have to do that because weather takes care of it. It falls in the mountains and we just collect it as it flows downhill. You guys not know any of this stuff? Good night. Matt, how do these kids survive?
You know, I was wondering that this morning.
All right, so guys, what does that have to do then with batteries and voltage? Well, guys, here's the idea. Imagine that you're at home and you hook a hose up to your hose bib, the thing on the outside of your house, that's what those are called, and you open up the hose bib and water flows out of the hose, right? Okay, so guys, when water flows out of a hose, there are two things that you keep track of relative to that water flow. One is pressure. What's the other one? It's actually flow rate. So guys, you know what I'm talking about. Have you ever taken a garden hose and you put that little nozzle on the end of it and it constricts and it turns that water into a laser beam? You know what I'm talking about? You can clean your car with it and stuff. So guys, if you do that, what happens to the pressure of the water? Is it high or low? The pressure is very high, but have you ever tried to fill a bucket with that laser beam? You're there for like a week and a half, right? So guys, the trick is that when you've got that nozzle on, you've got very high pressure water, but the flow rate is very low. Does that make sense? So what are you going to do if you want to fill the bucket more quickly? Well, you're going to take that stupid reduction nozzle off, and then the water is going to fill the bucket more quickly, but what does that do to the pressure? The pressure goes down. So guys, we've got these two competing ideas, pressure and flow rate. Do you understand the idea relative to water? Guys, the same thing is true relative to electricity, but the units are different. When we talk about pressure for water, we measure that in PSI. Pounds per square inch if you're in America. Guys, when we talk about the pressure of electricity, because guys, maybe we should make the connection. I'm not going to take anything for granted about what you know. Water is the flow of water. Electricity is the flow of, oh, thank goodness. Okay, electrons. So guys, in the same way that water flow has a pressure and a flow rate, so does the flow of electrons in a wire. And so, first of all, pressure. There is a pressure that is pushing those electrons through the wire. What units do we measure that pressure in? Volts. That's voltage. Guys, voltage is the pressure pushing the electricity through the wire. So what about flow rate? You get the idea behind flow rate, right? So guys, what is the unit of flow rate in a wire? It's amperage. If you've ever heard of amps, that's flow rate. It is literally the number of electrons that flow through that wire in any given amount of time, in the same way that flow rate for water is the amount of water that flows through a pipe at any given time. So guys, how does this stuff all then fit together? Well, all you've got to remember is that electrical pressure, just like in a pipe, electrical pressure is voltage, and then guys, the flow rate is amperage. Does that make sense? Okay, so guys, with that said, we do not have to deal with amperage in here. The only thing that we need to worry about is flow rate, which is voltage. Or not flow rate, sorry, pressure, which is voltage. Does that make sense? Do you now kind of understand? The pressure of the electrons flowing through the wire. It depends. So yeah, so we have a minute, we can talk. So for example, lightning, okay? Lightning, we understand, will do us in, right? The trick here is that lightning is amazingly high voltage, relatively low amperage. And so lightning is a very high pressure flow of electricity, and the amperage is relatively low, and that'll do you in. But at the same time, I don't know if you've ever done this, but if you look at the other side of that equation, have you guys ever looked at the battery that's in your car? Yeah, so I'm going to try. What is the voltage of your car battery? Oh, who could it be? 12. 12 volts? 12, it's 12. But guys, have you ever looked at the amperage on your car battery? It's like 650 amps. Tons of amps. So let's put that in perspective. So guys, when you plug your iPhone into a USB jack, the voltage of that is 5 volts. What is the amperage? About 0.5. 0.5 amps will charge an iPhone. It will not charge an iPad. If you want to charge an iPad, you need more electrons. And so the iPad chargers are actually 2.1 amp chargers. Have you ever tried to charge an iPad on an iPhone charger? It takes like a week. The reason is because that 0.5 amp charger doesn't provide enough electrons to fill up the battery in the iPad. So you want the 2. Anyway, so 2 amps is a lot of current to charge a battery. So guys, the battery in your car is 650 amps. But you know what? If you touch the two, don't do this. But if you touch the 2 terminals on your battery, it won't kill you. Why not? There's not enough voltage. There's not enough pressure to push all those electrons through your body. Your body actually offers enough resistance that 12 volts is not enough to push that current through your body. So guys, death comes where you've got enough amps that there's enough electrons there to short your body out, but there's enough volts to push those amps through your body. Does that answer your question? Okay. Yeah. Well, yeah, or you can lick a 9 volt, right? I mean, if you lick a 9 volt, it'll shock you. If you put it against your skin, it won't, because it's not enough voltage to push. But if it's wet, it'll push, but then it's low amperage, and that's not enough to hurt you either. So it's a mixture of both. So guys, let's then relate all of that. We got to go. Guys, let's relate all of that to this. So what does this mean? Well, guys, let's pull this together, and this is going to get a little silly and playful, but don't miss the learning. So, guys, the idea is this. Find the 0 point. Where's your 0? Hydrogen. Hydrogen is the reference for all of these. Guys, you've got to understand what this is. This is a reduction potential chart. Reduction is taking in electrons, right? So guys, here's the way to think about this, and don't get distracted by the playful thought. Guys, reduction is taking in electrons, right? So what this table is a measure of electron sucking in power. So the higher you are on this table, the better you are at sucking in electrons. So guys, what's at the very top of the table? Why is fluorine at the top of the table? Because it's the most electronegative element on the periodic table. Doesn't that make sense? So guys, fluorine sucks in electrons with a voltage of 2.87. That is like super sucker power. But here's the thing, guys. That number, 2.87, is actually relative to hydrogen. So what that means is fluorine is 2.87 times better at sucking in electrons than hydrogen is. And guys, we choose hydrogen as our 0 point arbitrarily. Any of these could be our 0 points, but once we establish our 0 point, then we can use these numbers to compare to each other. Okay? Now let's talk about this. Go to the bottom of the table. What's down there? Lithium. But guys, look at the voltage off to the right. What do you notice? It's negative. Guys, what does that mean? What does it mean to have a negative voltage? Rebecca, do not miss this. What does it mean to have a negative voltage? It means that you are not an electron sucker-inner. You're an electron giver-awayer. Does that make sense? Yes. Because they're always written as reductions. We're going to talk about switching the arrows on Friday. Yeah. But for right now, and guys, so relative to that thought, guys, go to the very bottom of the table. What has an electron giving away power of 3.05? The answer is lithium ion. The answer is not lithium atom. So, and that's why that's why batteries now are lithium ion batteries, because lithium is so good at giving up electrons. It makes a wonderful, we'll talk later, it makes a wonderful anode for a battery. Yeah. Well, they would slide. So say, for example, you chose nickel as your 0 point. See it down there? It's just a little bit below. Then you'd have to add 0.25 to everything.
Yeah, so those things that are negative
Relative to nickel. And it's all relative to your 0 point. Go ahead. We're not going to do that yet. That's Friday. I just need you to understand the numbers. We're going to talk all about why these numbers are true later on Friday. We will get there. For now, you just need to know positive values mean electron spitter, negative values mean electron taker inner. Okay. You okay? We will go over it on Friday. So guys, with that said, let's now develop this idea of how batteries work and how we can figure out their voltages. So I would be judicious about the notes that you take, but guys, the idea is this. Any surprises here? Oxidation is the losing of electrons. When we have an oxidation reaction, the electrons appear on the product side of the half reaction. Is that okay? Electrons are released or produced. And then guys, what you're going to find out today is that a lot of times, especially relative to batteries, when we talk about oxidation, we're going to talk about metal atoms losing electrons. When a metal, a neutral metal, when a neutral metal loses electrons, it then takes on a positive charge and then becomes soluble in water. That'll make more sense in a minute. Then guys, reduction is the gaining of electrons. Here, as we see on our reduction potential chart, the electrons are on the reactant side because they're being gained. And relative to batteries, what you're going to see is metal ions that are in solution. Remember, ions are in solution. Ions in solution gaining electrons and being deposited as solid neutral atoms. So guys, let me show you what I'm talking about. Consider this. You can scratch it in your notes if you want. Zinc plus copper 2 sulfate yields zinc sulfate and copper ion. Guys, here's what I need you to do. Write the net ionic equation, then write the half reactions. Do it now. And then guys, third, which is oxidized, which is reduced? This stuff is really fun to teach. This is cool. Wait until we start drawing batteries. This is going to make a ton of sense. Did you get it? So, goes like this. What's our spectator? Sulfate. So guys, sulfate is our spectator. Therefore, our net ionic equation is this. Is that okay? So let's then talk about our half reactions. If zinc is becoming zinc 2+, is zinc gaining or losing electrons? Losing. So that would be zinc yields zinc ion plus 2 electrons. Then guys, copper 2+ is gaining 2 electrons and it is becoming copper metal. So guys, which one of these is oxidation, top or bottom? Which one's oxidation? Top. If you're not sure, oxidation is the loss of electrons. There's the electrons that are being lost. Then conversely, the second one is your reduction because electrons are being gained. Now guys, let's tie this back to what we talked about just a minute ago. Guys, what does this look like? What does this look like? It's a solid, chunky metal, right? What does this look like? Dissolved in water. Get it? So when we have reduction, we've got a solid metal dissolving into water. Guys, what does copper 2 plus look like? Dissolved in water. By the way, what color is it? Blue. Then, guys, what does this look like? A penny. Get the idea? Here where we've got reduction, the ion that's dissolved in water is becoming a solid. So, with that said, guys, let me show you what this looks like.
When a zinc rod is immersed in an...
So there's our zinc. That's our zinc rod. There's our blue copper ion in solution. Let's zoom in.
aqueous solution of copper sulfate, a similar oxidation reduction
That's
reaction
what we just
occurs.
wrote. Notice it said similar. This is actually the second part of a longer video. So guys, those are the zinc atoms.
In this reaction, zinc is again oxidized.
There's our copper atom. So guys, this copper atom is missing 2 electrons, right? I'm sorry, the copper ion is missing 2 electrons. So that means this copper ion can gain 2 electrons. That would be the reduction, right? So guys, where is copper going to get 2 electrons? From the zinc.
Now,
So,
however, copper 2
They
plus
touch.
ion is reduced.
Let's do
to
that
copper.
again. They
Copper
touch.
2 plus ion is reduced.
2 electrons are transferred. When the 2 electrons are transferred, the copper ion becomes copper metal. It looks like a penny. Now, guys, what happens to the zinc? The zinc metal is now zinc ion, and what is that zinc ion going to do? Dissolve into the water.
to copper metal.
Get the idea?
In the 2 examples we have seen, zinc is oxidized. Because it causes the reduction of other substances, zinc is said to be a reducing agent.
We'll talk more about
The
that later.
substances that are reduced in these
Actually,
reactions.
we don't even need to worry about this. So guys, it's all about that exchange of electrons.
Now, however,
they
copper
touch,
2 plus
zinc
ion
loses
is reduced.
electrons, copper gains electrons, boom. You get it? Okay. Now guys, let me tee up for you the rest of the day. So it goes like this. Electrons, right? What's electricity made of? Electrons. So guys, here's the deal. We've got electrons flowing. This process causes an electrical current. The electrons flow from the zinc atoms to the copper ions, and as those electrons move, that creates electrical current. The problem is this, though that flow of electrons is worthless to us. Guys, we cannot harness that flow of electrons to do work because the flow is happening through contact. So what we've got to do in order to take this flow of electrons and put it to meaningful use, what we've got to do is we've got to separate these two. We've got to trick the oxidation, the loss of electrons from the zinc, and the reduction that's happening to the copper ion, we've got to trick them to happen in separate places. And if we can get them to happen in separate places, then we can connect them with a wire, and instead of allowing the electrons to flow through contact, if we can trick those electrons into flowing through a wire in order to go from one to the other, then we can harness that flow of electrons to do work, and guess what we just made? A battery. And guys, that is what this is. Grab this sheet of paper. Guys, this is fundamentally what a battery looks like. Notice right now that you've got 2 different cells. Do you see it? You've got a bucket on the left and you've got a bucket on the right. Guys, those buckets are actually the places where we are going to cause these oxidations and reductions to take place. So fundamentally, we're going to tear these apart. We're going to put the zinc on one side, the copper on the other side, and we're going to allow the oxidation reduction to take place, but we're not going to let them touch each other. We're going to connect them together with a wire. That's what the loop is across the top. And then as those electrons flow from the oxidation to the reduction, we end up with a battery. So what we can do then is we can put a motor in that wire, and that flow of electrons makes the motor spin, kind of like a water wheel. We can put an element in that wire that doesn't let electricity flow through very well, and when it does, it makes friction and it gets hot. Now we've got a toaster or a light bulb. See guys, that's what electricity is a flow of electrons, and depending on what we put in the way of that flow of electrons, we can get motors, we can get fans, we can get toasters, we can get light bulbs, all depending on what we put in the way of that flow of electrons. So, how does this work? Yeah.
That doesn't sound very spontaneous to me.
Well, that's about, all of these are spontaneous, and you're about to see why. Yeah, and that's where this is headed on Tuesday. So guys, it goes like this.
When a strip of zinc metal...
How do we make this into a battery? Well, look at what we're looking at. What's that piece of metal? Zinc. What's in the water? Copper. How do you know? It's blue, but it's not copper. What is it? Copper ion. Here we go.
...is immersed in an aqueous copper-2 sulfate solution. Electrons are transferred from zinc to the copper-2 ions.
Guys, notice what this does after about 5 minutes. What is the chunky stuff on the zinc? Copper metal. What happened to the blue tint of the water? It's less blue. Why is it less blue? Because the copper ion is no longer dissolved in water. It's now plated out on the zinc. But guys, what about this? What if we could rub all the copper off of the zinc rod, the zinc plate, and what if we weighed it first and then weighed it after? What would happen to its weight? It would go down because the zinc atoms are losing electrons and going into solution. So now some of these zinc atoms are in solution as zinc ion, and as a result, the zinc plate is getting lighter because the atoms are going into solution. But again, guys, this is not a battery. Why isn't it a battery? Because the exchange of electrons is happening through contact.
Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc 2 ions, which enter the solution. This spontaneous oxidation reduction reaction is summarized in the chemical equation shown.
Look familiar, right? Okay, here we go.
The spontaneous...
Aha! You see it? Grab the picture I gave you. Guys, here's what's going to happen. We are going to play through this video and we are going to talk about how separating these two cells, you'll find out into an anode and a cathode, creates a battery. We're just going to let the video play through so that we get a sense of this, and then together we're going to take that paper that I gave you and we're going to label it, and we're going to talk about all the chemistry that goes on that you're about to learn about. So here we go.
Copper-zinc oxidation reduction reaction can be made to yield useful electrical work by incorporating it in a Voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper-2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper-2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called...
You notice she got that wrong? It's not the reduction of copper, it's the reduction of copper ion.
the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a Voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode.
Got it? Let's piece it together. Here we go. Grab your papers. It is confusing. That's why you pay me the big bucks to teach you. Here we go, guys. Let's label our parts. I'm going blue. Oh, yeah. But not in this. It changes all the time, but not for this. So, guys, feel free to write down everything I write up here because this is what we're going to talk about. So, guys, we've got zinc on the left. We've got copper on the right. So now that we've done this, let's first of all talk about what else is inside of these cells. So guys, in addition to these things, which are called electrodes, one being a strip of copper and the other being a strip of zinc, these are also soaking in solutions. And what are these solutions made of? The metal, but then dissolved, right? So it's the metal ion. So in this case, it would be zinc ion, and in this case, it would be the copper ion. Now guys, you'll notice that I left out the sulfate. Why did I leave out the sulfate? It's a spectator. And we saw that, right? That's why I had you balance. I gave you that balanced equation and you wrote the net ionic equation to bring out the idea that the sulfate is a spectator. Now guys, with that said, I am going to include the idea up here that sulfate is a part of this cell. And we'll talk more about that salt bridge in a minute. But if you're actually building a battery, what you're going to do is your salt bridge will contain the same spectator ion that is in your cells. And we may as well just complete this. And then we may as well grab sodium. Why sodium? It's negligible. It's soluble, but it's not acidic or basic. So it doesn't do any chemistry. It just dissolves. Okay, so now, guys, we need to start talking about what's going to take place here. Now, in the previous slides, and maybe we should write this down, remember the chemistry that we wrote down. Oh, gosh. I'll put it up here. So we started with solid zinc, and we reacted that with copper ion. And when we did, we ended up with zinc ion, and we ended up with copper metal. So that is the reaction that's taking place. So now, guys, and if you need to refer to your notes, feel free to do that because you've already written the half reactions. But guys, remind yourself, if zinc goes from 0 to +2, is it being oxidized or reduced? It's being oxidized. So let's write that down underneath the zinc cell. So this is zinc going to zinc 2+, and that is releasing 2 electrons. That is our oxidation half reaction. Then, guys, let's go over here and let's represent the reduction half reaction that we've already written, which we can now assign appropriately to the other cell. So now, guys, with that done, we can talk about how this battery leverages this chemistry in order to produce useful current. So, guys, again, what is happening over here? Oxidation. Oxidation is the loss of electrons. So let's label that. This is our oxidation cell. Then, guys, over here in the right-hand cell, we have reduction, which is the gaining of electrons. So we're going to have oxidation take place on the left. We're going to have reduction take place on the right. So now, guys, let's draw some arrows. So we understand that oxidation is taking place. What is being oxidized? Zinc or zinc ion? Zinc is being oxidized. So, guys, look at it this way. As this happens, is zinc metal turning into zinc ion, or is zinc ion turning into zinc metal? Metal to ion. So, guys, this is going in this direction. Now, as it does, what else is produced in addition to the zinc ion? Electrons. And where do those electrons go? Those electrons go up the wire. That's an E, but not a very good one. So guys, these electrons go up the wire. Now hold that thought and let's go over and look at our other cell. So guys, over here in this cell, which way are you going to draw your arrow? If you've done things like me, does your arrow go left or right? Your arrow goes to the right. Copper ion is becoming copper metal. But now, guys, the question is this. In order for copper ion to become copper metal, what do you need? Where do the electrons come from? Over there. So, guys, these electrons go all the way around the circuit, and these electrons then end up over here. And if you think about how this works, doesn't this make sense? What does the charge of this electrode become if electrons move over here? Becomes negative, and if that's the case, the positive ions are attracted to it, right? Okay, so the electrons come around. So now, guys, we've sort of identified the flow that's taking place here. Now what we need to do is we need to give these cells names. So oxidation is happening over here. Let me say it differently. In the cell where oxidation is taking place, we give that cell a name, and it is what is called the anode. Then, guys, similarly, the other side where reduction takes place, we've got the cathode. How are you going to remember that? Anode and oxidation start with vowels. Cathode and reduction starts with consonants. If you can keep track of that, you'll be just fine. Okay, so now, guys, let's talk about this flow. So what we end up with then is we end up with the flow in this direction. But guys, here's the idea. We end up with a lot of electrons over here, right? Think this is very important. We end up with a lot of electrons over here, yes? Yeah, where did they come from? Where do all these electrons come from? From the zinc. So guys, that makes this the negative side. The negative side is where the electrons are most plentiful, and the electrons are most plentiful where they come from, which is over there on the left. So if that side's negative, that side's positive. Well, but remember, the electrons come over here, and as quickly as they come over here, they go to the copper ion. So this side is actually neutral because all of these electrons that are coming in are actually being consumed by the copper ion. Just leave it like this. This is the way we do it. If you understand the chemistry, don't get caught up in the why don't we do it some other way. Now, guys, check this out. What direction does current flow in a battery? Negative to positive. And I'm getting the sense that you guys never even think about batteries, which is sad. But if you ever have, guys, understand that if you grab, like, for example, a C-cell battery, I'm not even going to ask if you know, the little bump is positive and the bottom's negative. Guys, electricity does not flow from positive to negative. It flows from negative to positive. Doesn't that make sense, though? If electricity is a flow of electrons, and if electrons are negative, there are physically more electrons on the negative side than there are on the positive side, and so electrons flow from negative to positive. Does that make sense? Okay, now, guys, think about it this way. Why do electrons do that? Why do electrons flow from negative to positive? Good, it's spontaneous. Now, guys, why would that be spontaneous? Well, we've got a lot of electrons over here, right? We don't have as many electrons over here. And what are those electrons going to want to do? Even out. And when they even out, guys, literally what they're doing is they're flowing from a high concentration area to a low concentration area. Does that make sense? They flow from high concentration to low concentration. In the same, watch my hands. Let's do that again. Guys, they flow from high concentration to low concentration in the same way that water flows from high elevation to low elevation. You get it? Guys, that's why the current flows. The same reason that balls roll downhill. When you're at the top of a hill, you've got a lot of potential energy. When you get to the bottom, you have less potential energy. The same thing is true here. We have a high electrical potential where there's a lot of electrons. We've got a low electrical potential where there are fewer electrons, and the current flows from high potential to low potential. Yeah. Because these electrons are free and these electrons are tied up with the copper ions. So understand, it's not the number of electrons, it's the number of free electrons, because that's what current is the flow of free electrons. And here these electrons are free. The zinc metal doesn't want them anymore. So here zinc is going, here, take electrons, and it creates a big collection, if you will, of free electrons, a high potential. Over here, the electrons are not free. They're tied up with the copper ions as copper metal. So we've got more free electrons over there than we do over here. And that's what that table's all about. And we'll look at it in just a minute. Yep, that's exactly the idea behind this, Talmadge, is that we always flow from the place where electrons are more easily given up to the place where they're more easily taken in. Yep. Okay. So guys, are you? Oh, go ahead.
So do electrons ever go the other way, right? If it's
good. So yeah, good. Let's talk. Hey, because guys, this is important. Hear this carefully. Jake asked a good question. Do the electrons ever go in the other direction? And the answer is no. But, and there's a but. Guys, so could the electrons go the other way? They could, but if they do, then it's not useful for us as a battery. But guys, the problem is this. In order to complete the circuit, we need something negative to flow that way. We need a circuit. But what we do is, rather than allow the electrons to flow the other way, what we do is we allow the negative sulfate to flow the other way. So we need a negative thing to flow in the other direction to complete the circuit. And so instead of letting the electrons work their way backwards, what we do is we fill this salt bridge with a positive and negative ion, and this becomes the negative thing that flows the other way, completing the circuit. And then just to make it complete, the sodium ion, which is positive, does go the other way. But that's what we do. Instead of letting the electrons loop back around, we let the sulfate loop back around, and because it's negative, it completes that flow of negatives. Does that make sense about the salt bridge?
So, do the electrons from the zinc that go to the copper side, those electrons go to the sulfate?
No. So where do these electrons go once they hit this? They grab a hold of copper ions and they turn into copper metal, and now they're locked into the 3D orbital of copper.
Okay, so this is not a never-ending cycle.
No, because eventually you run out of stuff and your battery dies.
So what's the purpose of having that salt bridge?
Okay, think about it this way. If you had, and I'll just write it off to the side, imagine that you have a hose, and your hose is a complete circle. Okay, so the idea is that if you, wait, does this work? Not very well. So imagine that you had a hose that's a circle, but there was a break in the hose. The idea is, well, no, that doesn't work very well.
between two buckets, many goes between those two buckets as well.
Ooh, there you go. Yeah, but the buckets would have to be sealed. Yeah, but actually, you know what? We could do that. Imagine that you've got 2 buckets and they're sealed. And what we've got then is we've got a hose that comes out of here, goes through a pump, and then goes into here, okay? But they're sealed. You get it? They're sealed, okay? So imagine that the pump pumps in this direction. Is water going to flow? You know what? Let's put water moving in the other direction just so it lines up with our picture. This is actually, thank you. This is a great analogy. So here's the idea. This is completely full of water. This is completely full of water. Here we've got a pump. If we turn on the pump, does water flow? Why not? They're completely full. You can't put any more water in here than full, right? So what do you need? Well, you need another hose that does this. Now the water will flow. You need a complete circuit. This water has got to be able to do this. Okay? Well, the same thing's got to be true here. These electrons have got to be able to flow, but in order to complete the circuit, we need a complete circuit. But the problem is if we allowed the electrons to flow backwards, we would no longer have a worthwhile battery. So what we do is we put something else that's also negatively charged that flows backwards to complete the circuit in the same way that this does, but we allow something else to flow backwards so we're not losing that electrical potential. Go ahead. Does it do what? No, so when do batteries die? And that's the last thing that we're going to calculate in this class is when, but let's talk about it briefly. When do batteries die? And the answer is when they reach equilibrium. Let's talk about it, and guys, we need to talk about this, so let's do this right now. So let me ask you this. What is happening to the concentration of zinc ion over time as this battery runs? It's going up. What is happening to the concentration of copper ion as this goes on? It's going down. Here's the answer to your question, Rebecca. You ready? We have a ratio, Kc, product divided by reactant. Okay, so we have a Kc ratio, which is the concentration of zinc divided by the concentration, and this is Kc, right? Because these things are solids, they don't show up in the equilibrium. So this is a ratio, and what's happening to the value of that ratio? Well, this is going up and this is going down, so the value of this ratio is ever increasing, right? We have a competing ratio, and that competing ratio is the amount of electrons that are present. Initially, we're going to have a lot of electrons here and fewer electrons there, but that's why they flow. We have an imbalance in electrons. So now what we have is 2 competing imbalances. This imbalance is a lot of electrons over here and not many electrons over here. This one's the opposite. It goes the other way, and what happens is when the concentration imbalance and the electron imbalance set each other off, cancel each other out, the battery's dead. So that's the way this eventually ends. Yeah. Yeah.
It's not like sending 4 electrons.
Well, yes, because the sulfate already has more electrons. It's got the negative, it's actually -2, isn't it? It's already got the -2 charge. So it is ferrying electrons, but it's not the same electrons that are creating the current. It's electrons that it already has because it stole them from the sodium to begin with. Uh-huh. Yes, yeah, you can think of it that way. Or at least it's balancing the pressure. It's a pressure release, if you will. Yeah. You guys okay with these things? So now let's do one more thing, guys, and this is going to be messy. I pray I don't really screw this up. Guys, the question that we need to answer is this.
When a strip of zinc metal is immersed in an aqueous copper 2 sulfate.
Oops.
When a strip of 1.
Where did that number come from? So guys, we now know that when we build this battery, it will have a voltage of 1.10 volts. The question is, where on earth, and let's go ahead and write it in, guys, where did 1.10 volts come from? And this is how we're going to wrap up the day. So guys, in order to do this, let's look on here. Grab your reduction potential chart. So guys, and I would encourage you to do this. Let's just go ahead and write on here. Guys, find the two half reactions that we're talking about on this chart. So zinc is easy, right? There's only one. Guys, which of the copper half reactions are we talking about? Top, middle, or bottom? Middle. Okay, so guys, remember, these are reduction potentials, right? So let's gather this data together on our table. So looking at copper, you'll notice, guys, that the voltage of copper is 0.34 volts. So let's write that down. The reduction potential here is 0.34 volts. And you know what? I think this will be helpful if we very purposefully make that positive. Now, guys, let's go to zinc. The reduction potential for zinc is negative 0.76 volts. So guys, now let's talk about how we deal with these numbers. So check this out. What happens at the cathode, oxidation or reduction? What happens at the cathode, oxidation or reduction? Reduction. So guys, this number right here is the reduction potential for the half reaction that's taking place. I did what? Oh, did I seriously? Oh, sorry. Oh man, that would really screw us up. Here, let me just erase. I'm sorry. Okay, so here we go. So wait a second. So this is, this is negative 0.76. Tell me this one again, plus 0.34. Okay, so guys, let's do this again. So the idea is this. What is happening at the cathode? Reduction. So guys, this number right here is the voltage for that process. So what does that mean? And think about it this way. That means that copper ion sucks in electrons, right? Copper ion sucks in electrons. Make sure you don't miss this, Brandon. I don't have to explain it twice. So guys, that means copper ion sucks in electrons with a sucking pressure of 0.34 volts. So it's going, and it's slurping in electrons with a pressure of 0.34 volts. Does that make sense? Okay, now guys, let's go over here and talk. What is happening at the anode? Oxidation. So guys, if the anode is oxidizing, is the reaction that's on here the actual chemistry that's taking place? It is not. And so Talma just gets to what you were thinking. So guys, what do we have to do to make this half reaction match what we're talking about? Switch the arrow. But if we switch the arrow, what else switches? The voltage to positive, and now what is 0.76 plus 0.34 equal? 1.10 volts. Does that make sense? You get the idea? So guys, notice the way that this then works. And Talma just asked this question a minute ago. Why does the voltage flow in this direction? And the answer is because copper ion is a relatively good reducing agent. We know that because it's above zero. And then find out that while zinc ion is not a good oxidizing agent, zinc is. And so zinc will give away, zinc will give away electrons, and as a result, this battery flows in that direction. So what we've done to make a good battery is we've chosen one substance that's good at reduction, another substance that's good at oxidation, and as a result, one of them is giving away electrons well, the other is taking in electrons well, and that creates an effective battery. You get the idea? Okay, so now guys, let's do this. Grab your equation sheets. Sorry, I meant to have you grab these and then I forgot. So guys, grab your equation sheets and find this section. No way. It gone. There's no way. Here's 2016. It gone. That's so funny. Whose test is this? Somebody whose initials are HE. I don't even know. But here's the thing that's funny. Look at what they did. They actually wrote down the equation that I'm about to share with you because they realize they're going to need to know it. This is so weird. But guys, let's pull this together as a unified equation. You shouldn't need this on the AP test because the agreement, the gentleman's agreement, is that they won't have you use equations that you don't have available on the equation sheet. But I think you'll find the logic makes sense. So guys, look at what we did. What is this number? What is that number? A reduction potential. And the reduction potential for the cathode we left alone because reduction happens at the cathode. Guys, this was originally negative, right? What was that number? The reduction potential at the anode, but at the anode, reduction doesn't happen, oxidation happens, so we had to switch the sign of that. Does that make sense? So guys, what we have then is a general equation that simply goes like this. It says that E cell, which is the voltage of a cell, is equal to the, how do we write this? It's not even on the equation sheet anymore. It is in the book, but you know what? I forget how we denote half reaction. Oh, we just go like this. We go E naught reduction. Sorry, let me write this. Yeah, reduction at the cathode. Because guys, remember reduction happens at the cathode. And from that, we will subtract the reduction potential at the anode. Now guys, why do we subtract from the anode? It changes the sign. So guys, there you have it. We have now gone over all the chemistry, all the logic, and all the math that you need to know about voltaic cells or batteries. Let's do questions. It depends. It could be many different things. What is the, so lithium is good at being oxidized, right? So wait, lithium's at the bottom. That's a reduction potential, which means it's actually good at oxidation. So what is the cathode in a lithium ion battery? Battery University. Lithium-based batteries, types of lithium batteries. Carbon. So one is carbon. Cobalt, manganese, phosphate. Interesting. Hey guys, so can I give you my little 2 cents on this? Hey, so if you find this stuff in any way interesting, can I just plant a seed with you? I really don't think there is anything better that you could do with your life, if you're interested in physics and chemistry, than design batteries. Seriously. Guys, you understand that if you really want to change the world in a positive way and frankly get filthy rich while you're at it, which typically are not the same thing, guys, build batteries. Because you guys understand this, right? You're starting to see solar panels on everybody's roofs. Guys, do you understand that we have the technology right now to run our entire country on solar? Why doesn't it work? Nighttime. Guys, solar does not generate electricity at night. We could go wind, but wind does not generate electricity when the wind's not blowing. Guys, we do not have an energy production problem. We have an energy storage problem. And if you can figure out how to store electricity on, they call it grid level storage. If you can figure out grid level storage, you'll change the world. You could fundamentally change the world, guys. And it's interesting. I would maybe after the test we'll watch this TED talk. There's actually this TED talk where they got together. This guy reporting was at the conference. They got together like the 40 smartest people on the planet in economics, science, everything else, and they just started spitballing in this room. And they said, "What is the biggest problem that our world faces right now?" And they're writing down things like starvation, drought, war, all these other things. And guys, the thing that's amazing, after they completed this list of like 10 things, every single one of those problems could be solved by being able to get access to cheap, clean electricity. Pollution, all of that. Why do we fight wars? Guys, regardless of what people tell you, we're fighting over oil. Right now, that's what we do, is we fight in the Persian Gulf because we want oil. If we could take care of that, it could take care of the problem. Why do they fight in Africa? They're fighting for land and resources. Guys, we don't have a shortage of water. Do you understand that? The water is there. We just can't move it around because it's too expensive to pump. We don't have a shortage in food. The problem, we have a shortage in distribution. And guys, we could solve every single one of these problems. I mean, man is a mess, and if we'll figure out something else to do wrong. But guys, seriously, we could radically change the world if we could figure out how to generate and store electricity cleanly. And guys, the problem is storage. So remind me after the test and we'll watch these videos, but it is fascinating. So guys, with all of that said, here's your homework. And seriously, one of you has got to do this for me. Dedicate your life to building batteries, because they'll change the world. It's pretty cool stuff.